Good afternoon. Good afternoon, and welcome to the Concrete Institute of Australia. I'm John Nichols, Technical Manager for the Institute. It's my pleasure to be your host for this afternoon's webinar, NEXGen Durability, Life Assessment, Bridge Durability, and Self-Healing. This webinar features three young speakers from NEXGen who will talk about three aspects of durability: testing and assessing remaining life in structures, durability of concrete bridges, and self-healing of concrete. The speakers are Jessie Ratcliffe, Yogesh Ramu, and Hansen Prasetyo. I'd now like to extend an invitation to Liam Martin from our NEXGen group to introduce our speakers. Ladies and gentlemen, please extend a very warm welcome to Liam Martin.
Thank you, John, for that wonderful introduction. My name is Liam Martin. I am a doctor at the University of Technology, Sydney. I've just recently finished my PhD, and I am also a young member for New South Wales for the CIA NEXGen platform group. And today I'll be your host for this durability webinar, covering life assessment, bridge durability, and self-healing for our three panelists, Dr. Jessie Ratcliffe, Dr. Yogesh Ramu, and Hansen Prasetyo. So thank you, everybody. And today I'll introduce our first speaker of the day. Dr. Jessie Ratcliffe is a senior engineer at BCRC. She's worked in material consultancy for 5 years. Following her PhD, she has started her careers as a graduate at GHD, currently working at BCRC, where she is involved in durability inspections, assessments for a wide range of structures, including bridges, walls, and buildings. Please welcome Dr. Jessie Ratcliffe.
Thanks, Liam, for the introduction. Afternoon, everyone, and thanks for tuning into this talk. I can get... There we go. Today I'll speak a bit about the purpose of remaining life modelling in reinforced concrete structures and what testing we need to complete to collect data about the current state of our structure and use that as a basis for our future predictions. We'll look at a basic model and the steps between our site tests and calculating that remaining life. So we can have different reasons why an asset owner might want to investigate our current condition and then model the remaining service life. We may want to know the remaining life of buildings or bridges that were constructed prior to the existing design codes, therefore may not be compliant with current requirements, or for which we have limited information. Like we know drawings often get misplaced, or they're lacking key information, or that one guy who knew everything retires. It might also be a limited inspection history, so we don't fully understand how the structure has been performing during service compared to the design. In other cases, we may be asking a structure to continue service life beyond what would reasonably be expected as the original design life. This could be for heritage reasons, like these 100-plus-year-old concrete bridge piles on the side here. Or we may also want to keep the older structures for sustainability reasons. So why replace a structure and consume new materials when the existing thing is still fit for purpose? Adding on to that, keeping the old structure may be able to reduce costs. Our on-site tests and modelling can be used to validate our design assumptions using actual service data and can provide updated service life if the service conditions change. For example, our changing environment may be affecting the structure differently. We may have load changes because our cars and trucks are getting bigger and we're asking our structures to do more. Or maybe there's damage which wasn't accounted for in the design stage. I'm sure whoever designed the Montague Street Bridge didn't expect it to be hit by a truck every other day. So here's a couple of examples of structures that we've investigated. First, we have a Victorian bridge built in the 60s. So if we go by current Australian Bridge Code, our service life should be around 100 years, but that code wouldn't have applied at the time of construction. This bridge crosses a river close to the river mouth, so it's tidal and the water is slightly brackish, which brings a risk of chloride-induced corrosion. And we have the the asset owner did notice a couple of minor defects that they felt were worth investigating. So the asset owners could be interested in knowing how much longer this structure would be useful for service and the first future infrastructure upgrades, such as the larger trams, because this bridge carries trams, that Melbourne is introducing. This other structure is a university building from the 70s that Uni plans to upgrade. The reinforced components didn't have any noticeable defects, no cracks, no spalls, but the existing drawings didn't mention the service life that was originally intended and indicated that a low strength concrete was used for some components such as the external columns. So the structural engineers that were designing the upgrades to the structure wanted to know sort of what they're working with, what they're starting from, so they can ensure that the upgraded building has an appropriate service life. So they've put in all that effort and can keep the structure for a long time. Step 1 of our testing and modelling is the visual inspection non-destructive or semi-non-destructive testing. In addition to visual defect mapping, you might complete half cell potential mapping or delamination testing, other tests to hone in on areas of interest. These defects will sort of be mapped against the exposure seen on site. Got an example of our sort of information capture. The map's redacted, but all the defects are sort of tied to drawings or GPS locations. So we can decide where we're going to test for future information. Key tests we need to complete to understand the deterioration state of an existing reinforced concrete structure is the carbonation depth. So carbonation is the reduction of pH, also known as neutralization of the concrete due to ingress of carbon dioxide from the atmosphere. During this process, carbon dioxide infiltrates the concrete, reacts with the calcium hydroxide and the cement paste. We've just got some equations outlining this process here. And overall, that reaction lowers the pH of the concrete. So the original high pH is what protects your steel and passivates it, preventing that corrosion from starting. It's just sort of illustrated on the right here in the Poor Bay diagram. You can see in the potentials for steel, we have a passive section that correlates with the pH of concrete, and as we move left, we have that chance of corrosion. So we test for carbonation using a 1% phenolphthalein spray. The spray is just a pH indicator that gives this lovely pink color when applied to uncarbonated concrete, and then it turns clear where the pH is below about 10. The spray is applied onto fresh concrete, so either a core sample that you've taken and then split, or a hole that's been drilled and cleaned out. We can then measure the carbonation front, that's the interface between the two colors. The picture on the right just shows you the importance of selecting your carbonation core locations using that initial inspection. So this one's been done over a defect that was noticed, and you can see that the crack has allowed the carbonation front to locally progress a lot deeper, and so we might expect accelerated deterioration in that area. We're also interested in the chloride profile of the concrete, that is the amount of chlorides present at different depths towards the reinforcement. Chloride ions enter the concrete by diffusing through the pores or through cracks, such as mechanically induced or shrinkage cracks. And then when the chloride ions reach the reinforcement, they can induce corrosion. Similar to the carbonation, they're thought to disrupt the passive film on the steel, reduce the pH level of the pore solution, and serve as a catalyst for oxidation of the reinforcement. Chloride-induced corrosion can be particularly aggressive in marine environments, but it's also an issue further inland where wind can carry chlorides. Magnesite toppings might exist, or chlorinations for pools and roll salt can give you those chloride ions. We test for chlorides. We take a concrete core sample. The sample's location should be selected based on that problem-oriented approach using the inspection, or the half cell potential map might show you areas where we have a higher chance of corrosion occurring and should be investigated. We can test using a silver nitrate solution sprayed onto the fresh concrete and exposed to UV light. The color change produces sort of this blue-gray discoloration at the top, where we have chloride ions, and then leaving a dark brown color where it's non-chlorinated. This core also has a pheno spray applied, which is why we sort of get this Neapolitan effect because we're doing both tests. This test is fairly quick, but it doesn't tell us the specific amounts at each depth in the core. So to find that, we need to do lab analysis where we grind up each level and find the amount of chlorides via titration. This gives us quantitative information on chloride levels that we can use for our modeling. The next piece of information we need is the concrete cover to Rio. It's because the cover is the protective layer between the steel reinforcement and the chlorides or the carbonation or any other aggressive species that might be present. Once data is collected, we can assess the cover for the element or for the structure, and how we present this information actually varies based on the project. So we can consider minimum cover if it's a critical element, or we want a particularly conservative assessment. But that might be overly conservative if you just have like the one bar that's sitting a bit high and can be treated locally. Median and average are more common, but you could misrepresent the risk in the structure if the cover is very variable. And so often we use the 95% confidence interval cover found via statistical analysis, and that covers sort of most conditions in the data set. In addition to our key condition assessment data, there are a few other factors we can measure while we're out there, including our cement content. If we're finding our remaining life based on chlorides, this is important because we are looking for 0.4% chlorides per weight of cement, not per weight of concrete. So we need to know that cement content. We can also look at the reinforcement, do a breakout, particularly in areas that have those defects that we noticed in the first stage, and assess any corrosion on the reinforcement, measure the size, and see if it's a plain bar or deformed bar. Can also consider measuring sulfates if our exposure suggests that might be a problem, and find structural details such as compressive strength of the concrete and the bar diameter. Could also, if you think there's a risk of alkali aggregate reaction or something else, you can take petrography cores. Cores are also great for checking things like voiding and compaction in the sample. We have a really great example of some interesting compaction on the right here. Cool. So now that we have our field data, we can start with the actual modeling. Our early service life estimates were just based on the square root of time approach and empirical data, sort of experience, to give us a minimum cover of concrete that should delay the onset of corrosion. So over time, that's been refined into deterministic models and full probabilistic models. One of the documents that explains these principles of service life design and calculation is the FIB Bulletin 34 model code. And this document presents strategies for service life design of concrete structures, including the concept of chloride-induced corrosion, modeled by diffusion through concrete according to Fick's second law. When the corrosion is caused by chloride ingress, the service life is usually assumed to be equal to the initiation time. So when that steel is depassivated by the chloride and corrosion can start. We don't really consider the propagation, so the actual corrosion and spalling carrying on, because that can be relatively short in duration compared to the life leading up to that point. And don't really know, there's a lot of uncertainty around the consequences of localized corrosion. So exactly where that spall occurs could make it critical or a non-issue. So we don't consider that section. Our initiation time, so our start of corrosion, is calculated using the apparent diffusion coefficient, which we'll calculate in a second. Our surface chlorides, thickness of concrete cover, which we've already talked about, and the critical chloride content, that 0.4% weight of cement. I think I'm taking too long. So our first one is the apparent diffusion coefficient, which is our chloride transport properties. It's the equation there. We'll show it on a graph shortly, which is much easier. Our critical chloride level is the amount of chloride at that reinforcing bar that we consider to be when it's likely to start corroding. It's typically taken as 0.4%, but different reviews and studies show, including the benchmarking FIB Bulletin 76, that is a fairly wide range. So it depends on your reinforcement, it depends on your structure, but the 0.4 weight percent is what we'll be using today. So that chloride level is our service limit state. So that's where we're saying that the structure has passed beyond what we accept to keep it in service. And that is defined by the asset owner. So it's whatever they're comfortable with. The 0.4% weight percent chlorides is commonly used, but it doesn't have to be that. And usually when people are thinking end of life, they might automatically jump to, is my bridge going to fall down? No, because we're considering a service limit. We don't ever want to get to the point where it falls down, which would be the ultimate limit shown on the right. These have nothing to do with the examples shown at the start. They are just pictures from online. This is our equation from the FIB model code that we'll be using. You can see how our apparent diffusion coefficient slots in, and when this chloride content at the depth of reinforcement reaches the critical, that's what we're calling end of service life. So to show how this all works, I've got a bit of example data. So say this is our core and we've sliced it at the level shown on the left. We have this chloride data as weight of cement. We can plot it. You can already see a curve sort of appearing. And then using our equation from the model code and the least squares method, we can fit that curve and find our apparent diffusion coefficient. So that is based on site data. That's not the diffusion coefficient that would have been measured at construction or present in your spec or your mixed design. That's based on what we've really found. And using the equations, we can then take our diffusion coefficient and calculate curves for the chloride amount at different times using the current age of the structure, the average temperature, either from BOM or from site measurements, and then the aging coefficient. And we finally get to our final plot. So we have a plot of our current chloride levels, so heading towards the reinforcement cover being represented by the vertical dotted lines. That's our average and characteristic covers. You can see initially we're nowhere near our critical level of 0.4 weight percent of cement. However, after 50 years, that's our yellow line, we are getting pretty close. We might be considering that in localized regions where we maybe found a higher bar with less cover, we could consider be considering some issues. And then our service life ends at when the structure is 125 years old, 90 years on, where it intersects our average cover. So what do we use this data for? Now that you know your service life of your structure, well, our example of the university, they have opted to do for additional testing that creates more representative data and can be used for a full probabilistic model, which is often less conservative because they want a little bit more certainty before they move forward. You might use the data to focus on problem areas, engage in repair and strengthening if it's approaching sort of end of life, but you want to keep it going. Or in the case of, say, our 90 years left, that seems like plenty. We can just use that for proactive maintenance and planning of costs so we know when we're going to have to start thinking about replacing the structure based on that knowledge. And that's useful for asset managers who want to work proactively instead of reactively. And that's it. Thank you very much.
All right, thank you, Jessie. Thank you for the such a comprehensive presentation on life assessment. I remind the audience that Q&A questions can be posted in the Q&A box down below at the bottom of the Zoom screen, and they will be answered at the end of the webinar event. We now turn to our second speaker of the day, of the afternoon. Dr. Yogesh Ramu is an experienced engineer at BG&E. He has 6 years of experience in civil engineering materials. He has completed his PhD in civil engineering at the University of Technology, Sydney, contributing to Australia's understanding of delayed ettrinite formation in precast concrete structures. He has authored several research articles on concrete hydration and DEF, and his work interests include cement chemistry, supplementary cementitious materials, concrete mix design, cement hydration, durability, and deterioration mechanisms. In the past, Yogesh has worked for Larsen & Toubro, MYK Laticrete, and currently Yogesh is an experienced engineer at BG&E, whereas work involves preparing durability documentation, thermal control plans for concrete, and construction support for various infrastructure projects across Western Australia. His presentation today is on the durability of concrete bridges, AS 5100.5 provisions and their applications. So please give a warm welcome to Dr. Yogesh Ramu. All right, Yogesh, take it away.
Thank you, Liam, for the introduction. Good morning, everyone. Today, I'm going to talk about the recent changes happened in the AS 5100, especially the durability section. I wish to talk about all the changes, but due to the time constraint, what I will do is just I'm picking my favorite one, which is the class 4.1.1, which is talks about delayed aggregate formation, which happens to my PhD topic as well. So I'm interested in talking about that in this presentation. I will talk about what are the changes happened in this recent amendment 2 in the class 4.1.1. And to understand that clearly, I would like to talk you through the DEF mechanism and possible impact on service life and structural performance, and what are the factors that can cause or aggravate the DEF precipitation in concrete. And then I will talk through some of the research outcomes from my PhD to give a scientific backing about why these changes are made in my understanding, and not necessarily what the committee actually thought and worked. Maybe it's just my interpretation of why these changes are made. And also I will talk about some other researchers results outcomes as well to support this amendment 2. And then we'll talk through SCM's role in DF mitigation, and also we'll talk through why GP concrete having lesser maximum curing temperature allowance. And then we will wind up this presentation. Okay, so first, what are the changes that made in the 4.1.1 amendment 2? So until 2018 amendment 1, all the concrete mixes have to satisfy the 75 degrees Celsius maximum allowed curing temperature. Unfortunately, it wasn't differentiating between plain concrete mixes and concrete mixes with SCMs in it. Although the performance is actually very different from a SCM mix and then a GP mix in terms of strength development, in terms of heat of hydration and resistance to many durability issues. It actually doesn't differentiate. So also the another issue is it doesn't provide any method to justify it. I mean, approved method to justify it. That just says like if it is some analysis is provided to exceed the limit, is anyone with when there is no an approved method in the standard. So the welcome moves in the amendment 2 or now it allows only 70 degrees Celsius maximum temperature for GP mixes, but it's actually differentiate the GP mixes with the SCM mixes, which allows currently allowing up to 80 degrees Celsius maximum temperature. So provided the concrete has at least 25% silica, 25% fly ash or 40% minimum slag, or in a combination of silica fume and fly ash to certain percentages. And then if it is only silica fume, 8 to 10 percentage in the concrete mix. So to understand and make sense out of this amendments, what we have to know is to understand what is ettringate, what is linear ettringate formation first. So then we will talk through why this amendment make actually logical and scientific sense. So what is Ettringite first? Ettringite is one of the various high rates actually forming in concrete. So it's basically a calcium sulfoaluminate hydrate. And during the initial hydration phase of concrete, if it is precipitating, we call it as primary Ettringite. It doesn't harm the concrete. It's actually, in fact, have some benefits to the concrete. So that is not an issue, but the issue is like Ettringite is highly unstable when it comes to elevated when it comes to the resisting high temperatures. So if the concrete is actually hydrating at very high temperature, say for instance like anything above like 70 80 degrees Celsius, the ettringite can disintegrate, decompose to monosulfate um, and sulfide ions in the concrete. So what is actually can lead is um, I will just take the laser point to point out. So the black dots in the graphical representation that you see in the slide is actually represents monosulfate. So what this can happen, what it can do is like in the concrete during the surface life, when the concrete temperature is actually back to normal, and when there is a favorable situation for the alkalis in the concrete to leach out from the system, say for example exposure to water or something. So what can happen is like this monosulfates can react back with the sulfate ions to precipitate ettringite back in the system. So this is happening after the concrete hardened enough during the surface life. So doesn't have much of space in the concrete to precipitate freely, and it's actually a highly voluminous high rate to form in the structure. So you can see is like needle like structures in the graphical representation. So what it can happen is like this precipitation can push the concrete a little bit harder to to create micro cracks in the system. So eventually the cracking is bad. I mean, internal cracking is actually bad. So it can lead to durability related issues. That's why everyone talking about DEF. So what, like you said, it could impact the durability of structure. I like to explain it through a couple of examples. So here, this is actually a bridge pier from located in France. You can see the bridge pier is actually exposed to water, and you can see a lot of map cracking in the surface of the concrete. So when people actually taken out some samples and tested, what they have noticed is actually a lot of ettringite is actually precipitated between the aggregate and cement interface. So uh, this could lead to durability related issues and potentially reduce the surface life of concrete. And on the right hand side, this is actually a precast concrete sleeper from Sweden. Actually, you can see, I hope you can see a lot of cracks here in this precast sleepers. And when it is tested, it is actually have a lot of needle-like ettringite precipitated in the precast sleepers. So in general, people think DF can be an issue in precast concrete, but not in in-situ concrete. But it's actually not so true. Here, if you can see any concrete elements which is actually quite large can actually lead to very high temperature that can potentially decompose the laterite formation, and so can result in DF. So I purposely picked two examples, one from in-situ and from precast concrete. So you have to be mindful in both, not just in precast concrete. So some of the factors that could aggravate the DF issue in concrete or like cement factors. First, I will talk through cement factors. Um, so DF can be very problematic if the cement has anything about 4% or higher sulfate content in it, and relatively higher aluminate content, and then alkali is close to 1% in cement, and then sulfate to alumina ratio, if it is close to in the range of 0.8 to 0.8 to 1%, it can lead to highly expansive DF in concrete. Luckily, Australian standards is actually pretty good. It restricts the sulfates to 3.5, and then the alkali levels are restricted to 0.6. Typically, Australian cements has like 0.6 sulfate to aluminate monomer ratio, which is actually below the levels required to have highly expansive DEF. So from a material perspective, from a cement chemistry perspective, Australian cements are not that susceptible to expansive DEF, but it's not the only factor that can lead to DEF. As I mentioned earlier, concrete temperature, either it could be due to self-heat of hydration or steam curing, can be problematic. That's why this amendment actually restricting the temperature here 70 to 80 degrees Celsius. And then the service condition, if you remember the earlier example that I shown you, the concrete was actually touching the water. So exposure to water or high humid environment can lead to expansive DF by just by promoting leaching of alkalis from the concrete, at least in the cover zone. So I will talk through one example for in-situ concrete and then one example for precast concrete where the chances of DEF is pretty high. So this is one of the bridges currently under construction in Perth. This is actually a twin beam. I actually cropped just to show one beam of one beam in the in the bridge structure. So this is roughly like 1.8 meter deep, very large pour. It was planned with like 65 concrete mix, MPA concrete mix, which actually had like 65% of slag in it. Even if it is having like 65% slag, if it is starting around like 29 degrees Celsius, it can potentially reach up to 80 degrees Celsius. Sorry, this is actually not steam curing profile. This is actually a prediction from Series E 766. Um, so you can see like not necessarily only precast concrete can go up to very high temperatures. Even the in-situ concrete, which even with 65% slag in it, can go up to roughly 80 degrees Celsius if it is not controlled properly at the early stage. If it is not if it is like very large concrete element. So we actually managed to get this concrete done with 55 to 60 roughly degrees Celsius when it actually the construction happened with our control system, with our control systems, with our guidance. The site people were able to do this concrete with a maximum of 55 to 60 degrees Celsius. So the another example I want to point out is from a precast concrete producer in Queensland. This is actually this bridge girders are manufactured for the Legacy Way project. As you can see in the left side, the precast girder is actually very um, deep. It's like roughly 2 meters, and the concrete actually had like 25% fly ash mix in it, but still it gone up to 80 to 90 degrees Celsius um, when it is actually cured at 55 degrees Celsius. So high temperature in concrete is possible even when there is like SCMs in it, even when it is like in situ or precast concrete production. So DAF can be a very much a possibility here, but just with the temperature we cannot say very correctly. We need to have to analyze all the other factors like cement binder chemistry and exposure, everything we have to consider to arrive at the conclusion like it's going to be an expansive DF or just a DF sitting in the concrete doesn't do anything to the concrete. So in this section I'm going to talk about some of my research outcomes um, done with Australian materials to justify the Amendment 2. So I actually took this Legacy Way materials and did some research in it, like in the laboratory. So what we actually did is like taken the Australian GP Siemens and produced some laboratory mortar prisms and exposed it to 90 degrees Celsius curing and studied it for like 3-4 years. And you can see like the Australian commercial Siemens doesn't produce any significant expansion in it. So in laboratory specimens, like if there is an expansive DF, it is precipitating. It's going to give some expansion in the length comparator study. Um, so it doesn't have any expansion for Australian commercial cements. But if you see the chemically modified cement to have 4% sulfate and 1% alkali in it, like it started to give like very significant expansion, even like within like 50-60 days. And it's reached a maximum of like roughly 1.5 percentage for one cement, and for another cement is roughly like 0.8 maximum expansion. So why some cements is expanding and some cements are not expanding is have to do with the chemistry, as I mentioned earlier. Like I mentioned earlier, like Australian commercial cements are not that susceptible to expansive DF, which is a good news for us. And even with the um, high for sulfate and alkalis cements, if you replace that with like 25 percentage of fly ash, you can see we can actually eliminate the expansion even in the worst cement cases. So that's why adding SCMs to mitigate DF is actually is a practically viable option to do. And I will talk you through some of the differences in concrete microstructure for these two cement systems. As you can see here, the lab-made cement with high sulfate and alkalis, you can see a lot of ettringate is actually precipitating between aggregate and cement paste, and also within the cement paste as well. Whereas the non-expansive system, you couldn't able to see any ettringate getting precipitated between the cement and the aggregate interface. So safe to say it doesn't have any expansive DEF in the system, but uh, if it is um, having fly ash, the things are much more better. One thing is doesn't have DF band in the system, and the another benefit is actually if you can see it here, the red graphs is actually the mixes doesn't have fly ash in it, and the black ones are actually mixes with 25% fly ash in it. You can see that the Portlandite is actually um, um, is peak is higher for zero fly ash mixes, and for 25% fly ash mixes is almost nothing. So what actually happening is the reactive silica in the fly ash actually consuming this Portlandite to form additional calcium silicate hydrate, which is actually a denser and more impermeable and strength giving cement hydrate in the concrete system. So basically what the fly ash or any other slag, any other SCMs, what it does is actually it consumes lot of calcium hydroxide and precipitate that into CSH. So what is actually happening is like there are a lot of pore and refinement happening in the structure, which actually make the concrete less permeable, and also mitigates. Also, it's actually having very less ettering it getting precipitated in the system, so it mitigates the DF expansion as well. Is it only fly ash does it? No, like if you see from some of the examples from other researchers who studied the slag systems as well, you can see like the plain systems, plain GP system have very high expansion when it's cured at 90-95 degrees Celsius, but with 25 to 30 five blast furnace lag, you can see almost the expansion is eliminated here. And also, like I already mentioned, it actually leads to a lot of pore size refinements, and so if you can see in the right side, you can see the RCPT, rapid chloride penetrability test results, where with the increased slag replacement level despite Q'd at 80 degrees Celsius is actually having very low charge pass, which is actually meaning like very low permeability in the concrete samples. So that's why uh, that's why the amendment 2 is actually allowing up to 80 degrees Celsius, considering the fact it can lead to a lot of pore reinforcement, refinement in the concrete with the SCMs in it, and also it can potentially reduce the overall temperature, and also it can eliminate expansive DF in the system. Now we will talk through why possibly plain GP concrete mix is actually restricted to 70 degrees Celsius, unlike the 80 degrees Celsius for the SCM mixes. Here, the left side, if you can see, it's actually an outcome result from isothermal calorimetry, where you can see like two cement paste cured at 20 degrees Celsius is actually having very normal hydration graph there. But if it is like exposed to 60 degrees Celsius, cured at 60 degrees Celsius, you can see the heat evolution is much, much higher. At the same time, it's actually much accelerated and faster. So because of these like faster and hydration, it can lead to a lot of coarser hydrate formation in the system. What is actually coarser hydrate formation is actually the system is not pore refined really well, so it can actually be like very high permeable, and also it gives a lot of heat liberated as well. So here in the right hand side, it is actually adiabatic, not isothermal, adiabatic calorimetry results. If you see here, as we go from 360 to 500 binded content, you can see from 65 to 70 degrees Celsius rise in the temperature, and also it happens like relatively quicker than the 360 mix. So I think the message here with the 70 degrees Celsius restriction is actually two GP mixes only when there is when only when the concrete is actually a lean mix, only when the pore size is actually small. So whenever there is a large concrete pore or concrete with higher binder content, so the message is to avoid GP mixes altogether and to promote SCM in the concrete mix. So another issue is, like I already mentioned, without SCMs in the concrete, just with GP cement concrete, actually that as the temperature goes higher, it can lead to reduction in mechanical performance of concrete. As you can see here, the concrete samples actually from 25 degrees Celsius to 90 degrees Celsius is started to see a significant reduction in both dynamic modulus and resistivity as well. So if the same samples, if you test for a compressive strength, you will see beyond 60, 70 degrees Celsius, you will see a lot of reduction in concrete compressive strength as well. So as the temperature goes higher, the impermeability of the concrete is actually reducing, which again I mentioned earlier, like it's due to the causes hydrate formation. That's why if it is the concrete is expected to go beyond 70 or something, it's better to have SCMs blend in it. So it's not only me who did this. If you can see, some other researchers also try to explain it to some other test methods. If you can see, like from 5% to 5 degrees Celsius to 60 degrees Celsius curing temperature, as you can see, the porosity is actually keep on reducing as the degree of hydration is getting higher. But for the 60 degrees cured samples, even after the degree of hydration is beyond 90, the porosity actually remains roughly like 10 to 15%, which actually justifies why we need a lot of SCMs in the system. So for a concrete with similar heat profile, this pore refinement is actually much better, and the porosity can be very well reduced uh, by using SCM. So to conclude, so the massive concrete structural elements can easily go beyond 70 degrees Celsius even with SCMs. Uh, so the advantage with ACMs is actually it can mitigate even if this goes beyond 70 degrees Celsius. Mitigate DEF to go beyond 70 degrees Celsius, and also can help in the pore refinement as well. And also ACMs can help even if the cement is actually having much higher sulfates and alkalis in it by accident. If we are getting some cements from abroad and accidentally it has more sulfates in it, even in that situation, adding SCMs makes a lot of sense to mitigate DEF, and it makes a lot of sense to actually um, the amendment to have the 80 degrees Celsius mark, because anyway, like many of the larger concrete mix pores are gonna reach 70, 80 degrees Celsius, and when the concrete having SCM in it, the people should not get worried about DF or anything, as it have the tendency to mitigate attenuate precipitates in the system, and also can help the concrete make be more impermeable as well. In general, in theory, auxiliary cements are having low DEF risk because of low sulfate and alkalis in it. And also it makes a lot of sense to restrict the plain GP concrete mixes to restrict to 70 degrees Celsius, as it's susceptible to have attenuate precipitation as well, and also it has susceptible to have like coarser hydrates formation, which actually can reduce the mechanical performance like compressive strength, and can relate to highly permeable concrete. So it's a lot makes sense to restrict the temperature to 70 degrees Celsius. Thank you. Thank you for your patient listening. If you have any questions in the Q&A session, you can ask me. I'm happy to answer that questions.
All right. Thank you, Yogesh. Thank you. I think we'll quickly move to our third speaker in the time remaining that we have. Hansen Prasetyo is a PhD student from the University of Technology, Sydney. Hansen is originally from Indonesia. He has attained his Masters of Material Engineering from the University of Melbourne. Previously, he's worked in the automotive industry and has contacts in Indonesia, Japan, and Germany. His PhD study investigates the mechanisms of self-healing concrete towards improving durability. He hopes that this research will contribute towards solving the dependency of the modern world on concrete materials. His presentation title is on preserving durability of reinforced concrete through self-healing materials. So please welcome our third and final speaker for this afternoon, Hansen.
Thank you, Liam, for the introduction. I'll try to be as quick as possible to finish it within the time limit. My name is Hansen. I'm a student at UTS. Hi, everyone.
Do you have screen control, Hansen? Is that working for you?
No.
Controls just come through now, Hansen. So just here we go.
Okay, I can now. Okay. Right. I got the control now. Yeah, so just moving on. Well, as you all know, like concrete is the most commonly used building material, and this is because it's very convenient, versatile, can be poured and form freely, gives a lot of freedom for designers and engineers. The main characteristics of concrete is that its compressive strength is exceptional, it's strong, but on the other side, when subjected to tensile stress, it is rather weak. And so when men started using concrete, they had to build based on these qualities. The Romans, for example, used concrete in compression only. That's why they built their buildings, such as it has arches, and so that the geometry of the building makes it stable, and the stress that that is applied is only compressive, not tensile. But sadly, when we build like this, it makes it hard to span distances. So we had a revolution, and this was big. This was first of all, it's French Revolution. It happened in France. Joseph Mounier, a French gardener, came up with the idea to put steel bars in concrete when casting. Apparently, he was just trying to make his flower pots stronger. But now that we have this, using steel rods in concrete, concrete can now stretch and bend much better. It can solve the problem of the low tension strength. It can now bear the tension stresses, and a lot of other structures can now be built with concrete. Like, for example, bridges that we before that we always use wood to build bridges, and then we just ran with it. We built a lot of buildings that that needs tensile strength. All the modern constructions are made mostly using this super material. And sadly, that even though that we solved that problem with the tension strength, now that we have a steel bar in concrete, it makes it strong, but also makes it weak. Because, for example, look at this cross section of a concrete prism with a steel bar in it and a concrete cover. The problem with steel bar is that oxidation happens, and then it started to corrode. Some rust appears, and then expansions happen, crack happens, and then the structure is then compromised. Yeah, so the effect of chloride attack can be like severe, is as you can see in these pictures. When it gets to this level, the structure is no longer suited for use. So if before those colosseums lasted for thousands of years, now it only lasts for maybe 100, maybe less. And how to improve it? We must first see how deterioration happened in concrete. I think this was covered by Jessie already, but there's an initiation period and there's a propagation period. During the initiation period, deterioration doesn't really happen. It's just a buildup of chlorides in the concrete cover. And then when it reaches a certain threshold, it turns to a propagation period where exponentially corrosion happens, and the reinforcement start to give up. So the idea is to prolong this initiation period to be as long as possible. That way, it will be the propagation period will be delayed, and the surface life of concrete can be extended. And this research, my research is based on concrete self-healing. So so this is a well-documented phenomenon that happens when cracks happen in concrete, and then calcium hydroxide reacts with air and water to create calcium carbonate crystals. And these crystals can seal the pores. So for example, we can look at this graph. This is from another researcher. She's from UNSW, but she also made her research in concrete self-healing. So on the first day, when crack is induced, we can see that this crack is quite visible here, but on the third day, it started to heal up. And on the ninth day, the concrete is fully healed. The crack almost fully disappeared. So this phenomenon, the self-healing, we can be further enhanced with admixtures, and crystalline admixtures is one such product that can help us with that. These admixtures are already available in the market, and there's a lot of makers who make them. The idea is that it stays dormant in the cement matrix, and then when cracks happen, water and air will go into the cracks, and it will trigger the crystalline formation. So I took these pictures from a YouTube video of Penetron. That's one of the maker of crystalline admixtures. So in the cement matrix, when crack happens, you see water goes in, and then also air, and then it reacts. The crystalline admixtures react with it, and it creates this crystalline formation that seals up the crack. By sealing the cracks, we delay the chloride ingress and hopefully prolonging the surface life. So we try to prevent chloride from reaching the steel bar. There is a lot of literature already covering this topic. My focus will be on its effect to overall durability. I'm doing this with an uncracked sample at the moment to see the full effect of CA on the cement matrix. So to see the difference between concrete with crystalline admixtures or CA and without CA, we use different dosages of CA, and then we compare them using these tests. We use compressive strength test, and then density. Check for the density. We check for the electrical resistivity. I also did XRD and test on the pore solution. Okay, so the result of the compressive strength is that basically without CA, and then these are the mixes with CA, respectively 0.5%, 1%, and 1.5% of CA was added, and we see that the compressive strength is unchanged. That's good. Then it means that adding CA doesn't reduce the strength in any way. Also, we checked for the density, and I did this by doing a VPV test. The same thing here, without CA, and then some addition of CA, 0.5%, 1%, and 1.5%. There is basically no change here, which is good. That means the density stays the same with the addition of CA. And then with its electrical resistivity, and here is the first difference that we see. We see that the electrical resistance is decreasing when we add CA into the mix and yeah, this could mean something, but we'll talk about it at the end. But I also did X-ray diffraction to see whether the constituents of the solid phase how they differ from each other. And the reference, I had 2 reference samples, and then 2 samples with 1% of Ca added. And as far as my eyes can see, they are the same. There's no difference qualitatively. This is not a quantitative test, but as far as I can see, that they're the same. The solid phase is exactly the same. Well, it's only 1% of Ca being added, but for the moment we can say it's very, very similar. Diffraction patterns also is just the usual components of cement paste. There's nothing special that appears when XRD is done on the hydrated sample. Right. So since the solid phase are very similar, so we just need to check the pore solution. And from a pH test, it shows here that when we add more Ca, there's a slight increase in pH, which is small, but it's good because a higher alkalinity can help preserve the passivity of the steel rebar. I also did ICP OES on the pore solution as well. I just wanted to see what ions are in there. And from this result, I think the most interesting one is sodium. In the pore solution of my samples, I see an increase in sodium when we increase the dosage of crystalline admixtures. The other ions doesn't really show this clear of a result. So might have to think about what if there's a lot of sodium in our pore solution. We also did chloride diffusion. This also was done by titration. I think this is also similar to how Jessie did her test for chloride diffusion, and the apparent diffusion coefficients also measured using using Fick's law. So the result is weirdly we have an increase of diffusion, apparent diffusion, with an increase of Ca. So that's not good. That means that when we add Ca into the mix, and we have an increase in chloride concentration, while it's supposed to be doing the opposite. But keep in mind that these samples are uncracked, and the increase is not very significant, right? So, but ultimately we want to measure corrosion in the steel bar. So we did an electrochemistry test. I made this sample. So I just cast a steel bar, a reinforcement steel, inside concrete, and connect this reinforcement with wires, so we can measure the electrochemistry aspects of it. We put the samples in the chloride solution, sodium chloride solution. We did a cycle 3 weeks, 2 weeks in dry condition and 1 week in wet condition. After 1 year, so we did 18 cycles here. After 1 year, we see that corrosion progress faster in samples without CA. So in the chloride diffusion test, we see higher chloride in samples with CA, but also lower corrosion in samples with CA. That's bit interesting. This is the RP, this is the corrosion potential. And we can see that this line, the reference sample, the green one is the lowest one. So it has the least corrosion. Sorry, it has the most corrosion. But then again, after a year of testing, and it's still at around the lower moderate benchmark. It's not yet at this level where there is a lot of corrosion. So I am continuing this test for even at the moment even. So at the end of this measurement, I will break these samples, and then I will take pictures of them. This is an example. This is an image that I took of the samples. So we had some corrosion here. Using MATLAB, I made a code to pick up the pixels where it's brown, basically where the corrosions are, and then we create a mask using that code, and then we can calculate the percentage of corrosion. Well, at the end of the testing period, I will break all of them. I will visually confirm the corrosion, take pictures, and measure the corrosion using this code that I wrote. Okay. So to conclude, the solid phases mostly unchanged with addition of CA, but the composition of pore solution became a lot more ionic. Maybe I think that's a cause for concern, because we can see that electrical resistivity went down in samples with CA. Also, the high sodium concentration in the pore solution might skew the balance of other hydration reaction. The higher solution of chloride in samples with CA needs to be investigated. But I think it could be because what I did was a total chloride test. So maybe some of those chloride was bound is bound to something else, and maybe it was a mistake that to use acids to do the titration. If I do it with water, we could have a different result. So I'm doing that right now. We have a decrease of electrical resistance that I said before. This might be caused by the reactive pore solution, but it's a cause for concern because it means that electrons can travel more easily through the concrete. It means chloride can travel more easily inside the concrete. Okay. And then the next step in my studies, I will do this test with cracked samples, since now we characterize the CA samples without the cracking. We analyze the cement matrix. So I think it's good to move on to do these tests with cracked samples, and possibly a combination with other self-healing materials can be interesting as well. We can use some fibers. We can use super absorbent polymers. These are also some materials that is being proven to help self-healing. So using this research, I hope that in the end we'll have more ideas about how to prolong the initiation period to delay the corrosion of the reinforcement bar, and that way we'll have concrete with better durability. That's all. Thank you very much.
Okay, thank you, Hansen, for the wonderful presentation. Unfortunately, we are a bit pressed for time, so if people need to leave, that is okay. However, we do have a Q&A session at the end here. I know that there are already several questions posed from the audience and have been answered by our panelists. But I invite you all, please, any questions that you have to Hansen, Yogesh, and Jessie to please put them in the Q&A section as best able to, and we will answer them either here or later on via email correspondence. So thank you. Just another round of applause to our lovely presenters so far. Thank you. I see that a few Q&As have already been answered in the chat. I think I might turn the questions over to Hansen while we have the remaining time. There's quite a few questions in the Q&A from Jim, asking about, is this particular technique that you're using applicable to already pre-existing structures with material, with existing cracks? And can this be applied to load-bearing samples, or is it more of a free-form concrete structure? Can you read the Q&As in the text box,
Hi,
Hansen?
yes. Can this also apply to concrete? It doesn't mean that the concrete that's already been...
For a concrete that is already existing, an existing structure.
Okay, so there's another way. So how I'm doing it in the lab is that I mix the CA, the crystalline admixtures during the mixing, but there's also another way to use it, which is mixing the concrete, the crystalline admixtures in water, and then spraying it to the already existing concrete cover, and then the water will seep into the concrete, and then we'll have the particles of the crystalline admixtures inside the concrete. But that is, that will probably, I think from the manufacturer, they said that the more effective way to do it is with new concrete. So yes, there is a way, but probably not as good as new concrete.
Okay, thank you, Hansen, for that answer. I might just pose one or two questions to our other panelists while we have the time remaining. This is a question for Jessie. I know that she's already been very helpful and answered quite a few questions in the chat. So fair's fair. A question for Jessie, if she's still available. Are you?
Yeah,
I think
sure.
she's... Oh, no, okay, cool. Question for you. In terms of monitoring and ongoing remediation, how extensive do you see the applications of this? Like, how necessary? Is it a once per year, go out and inspect the field site, go back to your models, or more as a either more or less ongoing involvement do you expect?
That's depends where you're starting from and where you're going. Like,
Yes.
have you got an already 60-year-old structure that hasn't never been inspected and you're starting from scratch, or do you have a 15, 20-year-old structure that has an excellent inspection history? So we sort of know what we're starting with, and then are you getting us out to just quickly look at carbonation in a few spots, or are we doing a comprehensive, more representative sample of several different risk factors? I wouldn't expect to come back that regularly. Your structure will be Swiss cheese in no time. Hopefully, if we can work with you to plan the actual testing in a way that actually suits what you need going forward. It should be, you know, maybe not one-off over the life, but, you know, not within another 10 years or something.
Okay, cool. That helps clarify. I'm just a lowly PhD student. Well, now conferred. So thank you for that clarification there, Jessie. A question I'll put to Yogesh, the other panelist and host. I know that you've answered a question about how SEMs impact the risk of DEF. I would also ask you to see if you can expand that or extrapolate those results to other new types of cements that are occurring in the world. So more limestone or more calcined clay cements that we can see occurring in the future and are expected to help reduce the associated carbon emissions with concrete. Just ask for your opinion there on how DEF risk that you can see in light of SEMs.
Thanks, Liam, for the question. So in terms of like limestone cements, there are some already proven research studies which explains when limestone is in the binder, so the precipitation of monocarbonates is actually dominating in the system rather than etching it itself. So monocarbonates, monosulfates in the system is actually pretty much dominating when there is some limestone in addition in that. So that itself can reduce the impact of DEF in the system. So calcine clays, I haven't got a chance to work extensively with that, but from the research studies, we can expect similar performance like other SEMs like fly ash and slag in terms of mitigating DEF, because it's also works in the similar way of reactions, everything. So I think it's expected to be very similar, but I haven't personally got a chance to work with that in DEF.
Okay, thank you, Yogesh. Considering that we're a bit over time here, and I want to thank all our panelists again for their lovely time and commitment here. If there are any lingering Q&A questions from the audience, contact details are provided on the CIA website, or you can contact each of our panelists through their respective agencies. For Jessie Ratcliffe, that would be BCRC. For Yogesh Ramu, that would be BG&E. And for Hansen Prasetyo, that would be via the University of Technology, Sydney. So please follow up those contact details if you have questions still lingering in your mind. I want to give a warm thank you to all three of our panelists and to our backup staff in John Nichols, Josh Taplas, and Katja from the CIA, and as well for the CIA NEXGen platform for hosting this webinar. So again, a round of applause from our audience, please.